Hypothalamus artificial intelligence, high presence. High power 6.0 that is oriented to optimization models for planning and operation in organizations in the electric and gas sectors, following the principles of modeling in Industry 6.0, using MOS, mathematical models as a service, in the cloud. High GAMS IBM TD SYNNEX is the strongest alliance in advanced artificial intelligence modeling. Distributed Economic Dispatch? Lecture prepared by engineer Jesus Velasquez Bermudez, Ph.D. In 2014, IBM estimated that companies in the energy and utilities sector, which used big data and analytics, reported 23 times higher productivity than those that did not. Digital Industrial Revolutions. Today, the evolution of industrial revolutions is conceived as Industry 6.0 is completely changing the mathematical modeling of artificial intelligence. Now we can talk about orchestration of swarms of cognitive robots, and living industrial ecosystems. These two terms are new to most people, including scientists, even though they date back at least 15 years. Industry 4.0 is a consequence of the invention of the digital computer and digital automation. Its origin may be in 2011, and the result is digitalization and interconnectivity, smart factories, that is, cyber-physical systems. Industry 5.0, the first mentions date back to 2015, is humanization and close collaboration between people and cyber-physical cognitive robots based on artificial intelligence. The transition from Industry 4.0 to Industry 5.0 represents a paradigm shift. We move from an approach focused exclusively on technological efficiency to one that prioritizes human value, sustainability, and resilience. While Industry 4.0 sought to interconnect machines so that they could make autonomous decisions, Industry 5.0 seeks to make these machines work with people to enhance their creativity and well-being. Formally introduced by the European Commission in 2021, this revolution does not replace the previous one, but complements it under three fundamental concepts. Human centrism: technology should serve people, not the other way around. It focuses on improving the health, safety, and job satisfaction of workers. Sustainability prioritizes circular processes that reuse resources, reduce environmental impact, and respect the planet's limits. And resilience, the industry's ability to withstand and adapt quickly to global crises, such as pandemics or supply chain disruptions. Industry 6.0 currently has no date, as it is considered a visionary and conceptual phase that is still being defined, but which is based on intensive artificial intelligence. Total autonomy, biological symbiosis and industrial systems that function as living organisms. There are already examples of this situation, as is the case with smart grids and the Internet of Energy. Industry 6.0 focuses on the total symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. The fundamental pillars are integration of mathematics and artificial intelligence, to produce artificial general intelligence, AGI, with the ability to understand, learn and apply knowledge in any intellectual task, in the same way, or even better than a human being. Human-machine biology symbiosis, fusion of human intuition, advanced artificial intelligence, and biological systems, such as self-healing materials or neurocognitive interfaces. Cognitive and proactive autonomy, transition from predictive maintenance to self-regulation and regeneration. Systems not only detect faults but are reconfigured to avoid them altogether. Regenerative sustainability, beyond reducing environmental damage, systems are designed to actively restore and enhance ecosystems through real-time circular economies. And ethical and conscious governance, AI incorporates moral reasoning and transparency, ensuring that autonomous decisions are aligned with human values and planetary well-being. The technologies related to Industry 6.0 are mathematical modeling, translation of real-world problems into a mathematical language, such as formulas, equations, or graphs, to understand, analyze, and predict behaviors of complex systems. Generative AI and AGI, co-creation of workflows and autonomous design of products based on abstract objectives. Quantum computing, massive data processing for optimization of ultra-complex supply chains and molecular simulations. Human digital twins, HDT, virtual replicas that simulate not only physical processes, but also emotional and cognitive dynamics of workers. Internet of Everything, I/O, and 6G, ubiquitous and ultra-low latency connectivity that enables the orchestration of swarms of cognitive robots and devices on a global and even spatial scale. Industry 6.0. A swarm of artificial intelligence algorithms, that is the orchestration of swarms of cognitive robots on a global scale. One aspect that becomes fundamental is the lives of professional people. Although professional development normally evolves to its maximum level at the end of university, however, it is common for professionals to lose knowledge during the exercise of their work and reach low levels of useful scientific knowledge. In the example, after high knowledge developed at the university, the actual exercise is limited to Excel, which is fundamentally arithmetic. This is another barrier that must be overcome. Now GPT is the intelligent, and super-fast, consultation of what is recorded on the internet, which limits many professionals to this knowledge. In 2020 there was already an awareness that the impact of industrial revolutions could be negative, and that this is apparently still happening. Digital natives are the first children with a lower IQ than their parents. This originates in the scientific gap that is forming. The difference between a scientific life and a real and ordinary life generate a big chasm, not a gap. OpTex, Optimization Expert System, is the generative artificial intelligence created by HI that builds enterprise-wide optimization systems for global companies. An expert system, S, is a computer system designed to emulate the reasoning and decision-making ability of a human specialist in a very specific area of knowledge. It is one of the most classic and successful applications of artificial intelligence, AI, gaining great popularity between the 1970s and 1980s. Unlike traditional programs based on rigid algorithms, an expert system uses structured knowledge, rules, facts, and heuristics, to solve complex problems that would normally require years of human experience. OpTex is an optimization expert system that helps the mathematical modeler and the user of the models to manage them. The result is that OpTex manages mathematical models without using programmers. The image shows the structure of a traditional expert system, which incorporates a human expert, who possesses the knowledge, a computer engineer, specialized in capturing the expert's knowledge, and a user who doesn't have to be an expert on the subject. The computational architecture of the expert system integrates three parts: knowledge database, inference engine, and human interface. As an expert system for a scientific topic, such as mathematical modeling, OpTex is accurate and does not require synthesizing the knowledge of experts who may differ in their opinions, which facilitates the commissioning of the system. In practice, the human expert, with computer knowledge, is a mathematical modeler, and the implementation of OpTex is summarized as the intelligent management of the knowledge database. In this way, a non-expert in mathematical modeling can manage OpTex, without the need to build programs. Hypothalamus artificial intelligence. Presence. OpTex, Optimization Expert System. The optimization technology that allows you to assemble multi-problem mathematical models like a Lego game, using structured mathematical modeling. Can you imagine how? Imagination is the beginning of creation. You imagine what you desire, you will what you imagine, and at last, you create what you will. By George Bernard Shaw. OpTex, the expert system for optimization, is used as the way to develop and implement AWO solutions, in which multiple mathematical models converge, and can be connected via disk or cache databases, to form a monolithic model of the enterprise. Optex is the generative artificial intelligence produced by HI, which manufactures optimization systems for the entire company. Created in 1991, Optex is used by HI in the implementation of AO systems. Optex may be the only computer tool capable of integrating hundreds, if not thousands, of mathematical models, running on a parallel and distributed computer system. For those interested in learning more about Optex, HI invites to watch the video Optex, Optimization Expert System. The traditional process of mathematical modeling implies that programmers, usually mathematical modelers or data scientists, must make great efforts to implement complex optimization models. The actual process of mathematical modeling implies the use of cognitive robots that generate and implement complex optimization models. Making an enterprise-wide optimization system, integrating multiple large-scale models, using a computer programmer, is an impossible approach, because the programmer can only write a limited number of lines of good source code per period. Maintaining these models can be more complicated than making them, if there is more than one programmer involved in the process. Only a generative artificial intelligence can produce infinite lines of perfect source code in seconds. Normalization and standardization, the base of mathematical programming 6.0. The foundations of Optex database algebraic languages consider the algebra as a standard, to express the relationships between the different parts that make up a mathematical problem. It can be said that there is only a reduced way to write an algebraic equation. This is independent of the symbols that are used to represent the physical or logical relations. Additionally, if two algebraic formulas are joined, a new algebraic equation is obtained that retains the same structural characteristics of the original equations. This transitivity law may be extended to mathematical programming, MP, which in essence is a collection of algebraic elements. Then it is possible to join two MP problems to obtain a new MP problem. It is also possible to divide an MP problem into two MP problems. The multiple models are assembled like a Lego game, which can have as many groups of tiles as there are models. Resuming, if the formulation of algebraic expressions is normalized, it is possible to have a standard way of representing a mathematical model that can be understood by another mathematical modeler, making it a standard for formulating MP problems. Additionally, the combination, or division, of MP problems generates new MP problems, which can be solved using many optimization technologies. Therefore, to facilitate the development of models, it is convenient to establish basic principles, norms or standards, of modeling, in order to enhance the use of models and ensure that they remain current over time, thanks to conceiving as a dynamic structure that adapts to changes in computer technologies. This implies, previously to the implementation of mathematical models, establishing a standardization manual that guarantees the understanding of the mathematical model, by any professional knowledgeable about the subject. This fact will result in the portability of mathematical models and the significant decrease in the implementation time. Structured mathematical modeling is similar to assembling mathematical models like a Lego. A mathematical model stored in an information system can be conceived as the union of mathematical components harmoniously integrated. There are two types of components, or objects. Basic mathematical definitions, indexes, sets, parameters, and equations or constraints. Advanced concepts, problems, models, decision support systems, and artificial hypothalamuses. These components can be stored in a relational information system. It permits their handling in a modular way. Following the principles of relational information systems, and use structured query language, SQL, to manipulate the mathematical objects. This conceptualization is independent of optimization technologies, which allows to separate the formulation of the mathematical models from their implementation, using a specific optimization technology. The nuclear unit, the molecule, of a MP problem is the constraint, which is the result of integrating various types of atoms. Indexes, sets, parameters, and variables. Based on the constraints, more complex mathematical structures are built. Problems, sets of equations and/or set of subproblems, models, sets of problems and/or set of submodels, decision support system, set of models, and artificial hypothalamus. considering that the problems are defined based on sets of constraints. If the modeler has built a database of equations, such as an equation store, he can formulate as many mathematical problems as the combinatorics of constraints that can be assembled. Traditionally, a problem is conceived as a monolithic set of equations. Under a modular conception, equations are components that can be shared by multiple problems. The important thing is that each equation works properly. This correct operation will be repeated in all the problems in which it is incorporated. If a store of equations exists, constructing a problem is limited to selecting the equations that make up the MP problem, and/or incorporate sub-problems that already have associated equations. This monolithic approach is easy to implement, however it does not allow the use of large-scale optimization methodologies. If it wants to use high-performance computing technologies, based on parallel processing, it needs to divide the mathematical model into multiple problems that represent the most elementary components of the physical system. This produces a significant gain in the solution time, and in the understanding of the inner operation of the system. To solve the model, it is necessary to select a large-scale optimization methodology that defines the processing of information in each problem. For example, the figure represents a mathematical problem related to the SAND-OP, sales and operations planning, that may be constructed based on 8 groups of equations. Production, energy, maintenance, distribution, sourcing, human resources, financial, and sales and marketing. The view the systems, groups of equations, that must be included in the SAND-OP problem depends on many factors, because there is no revealed truth regarding what the SAND-OP problem is. Since the equations are defined in a database, the configuration of a problem is limited to selecting from the equation store which are the ones that the modeler want to consider in the model. These visions can change within an organization. In this way, the modeler can have multiple SAND-OP models which depend on the use you want to give to the models. These models can exist permanently, or they can be created on the fly at the time they are required to be used. A decision support system must group all mathematical models, predictive and prescriptive, that uses the enterprise. Therefore, a DSS can be defined by the set of models that integrate it. Associated with the DSS must be the flow of information between the models, since it is logical that the output of one model is used as the input of another model. The traditional is that these models are used by users in a manual way, except in cases of advanced optimal control in which the models can run permanently, in real time, in an infinite cycle. An example of the architecture of a production DSS in an organization is presented below. It is made up of 8 models. The diagram describes the data flow between models. Traditionally, these models are run with a certain frequency, daily, weekly, bi-weekly, monthly, and the implementation of the decisions depends on the professionals who must validate the results. In some cases, this validation is automatic. The model's interconnection chain has no limits, which is necessary for an organization based on advanced analytics. Industry 4.0, intensive in data acquisition, extends the concept of real-time to any hierarchy of decision-making. Generating the concept of autonomous, real-time, distributed, optimization, in which multiple agents, distributed in the space, cooperate to solve an integral problem of the organization. An agent may be a country, a region, a business, an administrative department. The multiples models can run autonomously, activated by an exogenous event, for example, an earthquake, the failure of an industrial equipment, or by another model that requires processing their data. The artificial hypothalamus corresponds to a macro algorithm that coordinates the activation and solution of the models defined by the mathematical modeler. From the computational point of view, the models correspond to a set of microservices that solve problems and produce the required information, acting simultaneously and cooperatively. Large-scale optimization methodologies are also solved using optext-structured mathematical modeling. Optext-structured mathematical modeling allows model cases using large-scale optimization methodologies, such as Bender's theory and Lagrangean relaxation. The concept of model integration is applied in multiple dimensions. For example, An integrated oil company can be conceptualized based on the operation of four businesses: production, crude oil transport, refining, and transport of derivatives. In this case, the complete model of the company corresponds to the integration of the four models. For example, the figure represents a mathematical model for a multi-business enterprise that operates three business: electricity, oil and gas. The integrated model of the company will be the union of the three super-problems. However, the modularity of the modeling allows to have individual models for each business. These models can exist as an integrated model, or as three individual models, one for each filial. In this case, the data communication for the integrated multi-business model is defined by the Lagrangean relaxation methodology. Under a hierarchical conception, each subsidiary can be divided into sub-businesses that can be planned in a coordinate or integrate manner. Coordinating, when each individual model connects with another model to send its optimal decisions resulting from an isolated planning. Integrating, when all models are part of a holistic model that produces the real optimal decisions for the enterprise. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus of the company is obtained. This is how the human brain faces reality. Multiple models of reality, acting permanently in parallel, to make decisions. The algorithm that simulates the hypothalamus is assembled by optex, using the models that traditionally make up a decision support system. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus of the company is obtained. This is how the human brain faces reality. Multiple models of reality, acting permanently in parallel, to make decisions. The algorithm that simulates the hypothalamus is assembled by optex, using the models that traditionally make up a decision support system. The image shows an artificial hypothalamus typical of Industry 4.0, which is based on an integrated problem, which is solved using large-scale optimization techniques. The coordinating brain can be associated with the master problem that coordinates all subproblems. Industry 6.0 focuses on the symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. Industry 6.0 is changing the mathematical modeling. Now we can talk about living industrial ecosystems, and orchestration of swarms of cognitive robots. This has led to the fact that, if desired, modeling in Industry 6.0 is autonomous, without human participation or coordination problems. Consensus algorithms are fundamental to the operation of decentralized networks. They ensure that all network participants agree on the validity of transactions. Without consensus, there would be discrepancies in the data between different nodes, which could lead to fraud and errors. These algorithms facilitate trust between users who may not know or trust each other. Different consensus mechanisms have been developed to respond to the needs of various applications, each with its own strengths and weaknesses. In the case of mathematical programming, the rules of consensus are exact. In Industry 6.0, modeling is more aligned with the artificial brain, which has organs that function autonomously and independently, without an explicit coordinator managing the process. Coordination is done using a consensus algorithm, which are mathematical rules, like Lagrange's theory, and not a coordination problem. If an enterprise-wide optimization system, EWOS, is defined as the set of tables that make up the mathematical modeling database, a super application, that is, an application composed of several basic applications, can be defined by joining the tables of the two or more applications, ensuring that the integrity rules of relational information systems are met. The diagram shows the integration of applications for the management of public health problems, which corresponds to a regional planning problem, as experienced during the COVID-19 pandemic. To address the problem, HI developed EWOS Health, an application for pandemic management, built with optex in 2021, and integrated it with EWOS HRPO, Holistic Regional Planning Optimization, built in 2006, implying that all models from the two EWOs can be used to build new models, through the mathematical modeling database, which uses a common data model for all models implemented in Optex, and/or through equations that integrate a single holistic model. Electricity system and wholesale market. Optimization models. There are many models that a company must use to operate in the electricity sector. To develop, implement and maintain high-power 6.0, is used Optex, Optimization Expert System, that it is the artificial intelligence created by HI that makes enterprise-wide optimization systems for the entire company. To develop, implement and maintain high-power 6.0, is used Optex, Optimization Expert System, that it is the artificial intelligence created by HI that makes enterprise-wide optimization systems for the entire company. Electricity system and wholesale market optimization models make up a flexible decision support system that provides different types of services in an integral way. They can be classified into integrated dispatch of generation plants, optimization of generating agents, and predictive analytics of stochastic processes. The models presented began to be built in 1995, all following the methodology of multi-problem mathematical models, which is the basis of today's artificial brains. They are the result of consulting and/or software development projects executed in real life. High Power is a decision support system that has been developed to support the decision-making processes of agents participating in the electricity and/or natural gas markets. High Power is composed of a set of optimization models that describe the supply/demand process of electricity and natural gas. From this point of view, it determines the partial equilibrium point of the electricity and gas markets under conditions of economic efficiency. Now High Power has included smart grid modeling. High Power is built following the principles of structured mathematical modeling, which are specific to Optex. Under this conception, software is built by means of layers of equations, which are integrated to build the models, which are part of a decision support system. In the case of High Power, it is an economic dispatch model, typical of the electricity sector. The diagram shows 8 of the many models available at High Power. Any of the models can be run in their deterministic or stochastic version, making use of asynchronous parallel optimization. For example, High Power has 4 models of dispatch of electrical systems. Economic dispatch, dispatch of electricity generation plants, minimizing the cost of operation of the interconnected system. Regulated economic dispatch, dispatch of plants minimizing the cost of operation, plus the regulated cost of the electricity market. It includes regulatory aspects of the electricity market. Nash-Carnot equilibrium dispatch, dispatch of plants oriented to the simulation of electricity markets, with 2 types of agents, price makers and price takers, and unit commitment, associated with operational planning decisions, related to the dispatch of plants by the hour, or more detailed periods. Linkage with planning via prices, or via quantities. 4 models are considered fundamental to support the strategic, tactical and operational decisions of an agent that operates generation plants. The models developed by HI for electricity wholesale systems and markets are dispatch models, economic perfect dispatch, economic regulated dispatch, Carnot-Nash equilibrium dispatch, electricity and gas dispatch, and unit commitment. Complementary models, electricity dispatch and financial analysis, maintenance of regional national grid, electricity supply chain design, and risk management, and energy trading and risk management. The video. High Power. Autonomous optimization software for electric sector enterprises. Presents more information about High Power. Operational planning and unit commitment. A well-known activity in the electricity sector is the coordination of 2 fundamental models. Economic dispatch, or operational planning, DP, and unit commitment, UC. 3 types of connectivity of the generation system and the transmission power grid are considered. Ideal single node, ideal dispatch ignoring the transmission system. Electric transmission network connectivity based on the detailed connectivity of the electricity transmission system using bars and circuits. Below, we will briefly and partially discuss HI's philosophy on the operating models it has used so far in the power sector, which can be used for an isolated smart grid. But with the arrival of Industry 4.0, technological change led to smart grids being considered autonomous and independent networks, which totally changes the modeling paradigm, considering that today there are no longer monolithic electrical systems. Attempting to model a smart grid network with traditional dispatch models is a major mathematical error. First, its size would be unmanageable in data and computer processing. Second, mathematics has changed to adapt to this new era. It makes no sense to use outdated mathematics, and third, it may be most important, it violates the philosophy of the new business and its regulation. All the models and methodologies developed for the electricity system and the wholesale market are applicable to smart grids, when analyzed as an independent system. It's just a problem of scale. Unit commitment, UC, associated with short-term operational planning decisions, such as the optimization of detailed distribution by the hour or for shorter periods, respecting all the constraints of the nonlinear and discrete system. The UC model is a mathematical problem that can be converted into nonlinear non-convex mixed optimization, which implies that it requires a special effort for its solution, since its real-time characteristic does not allow unfeasible approximations for its solution. On the other hand, it is necessary to coordinate the UC model with a medium-term planning, DP, model, which establishes the boundary conditions, in such a way that the state of the system at the end of the UC problem be the same as at the beginning of the DP problem. Below, we will briefly and partially discuss High's philosophy on the operating models it has used so far in the power sector, which can be used for an isolated smart grid. Ideally, a single model should be solved, which would allow the system to be represented in detail throughout the planning period, that is, solving a long-term scheduling problem during periods 1 to t. For complex systems, this may not be computationally viable. However, for not-so-complex systems the alternative could be viable, considering the computational capacity offered by Industry 4.0. For this reason, conventionally it has been considered necessary to resort to the integration of both models, UC and DP. You should consider the implicit approaches involved in such a decision. Based on the vision of the artificial hypothalamus, building a monolithic model consists of cutting and pasting equations, and thus obtaining the optimal solution, regardless of the type of dispatch model that is appropriate according to the market. The solution of the monolithic model can be realized with large-scale optimization methodologies. The traditional thing has been to divide the process into two models. Stochastic economic dispatch model, oriented to planning activities, and deterministic model of unit commitment, oriented towards real-time scheduling. The coordination of both models is essential for the results obtained for the real generation. The traditional way to approach the problem is to coordinate the two models, solving each independently, offline, so that the office planning model, DP, establishes the boundary conditions of the office scheduling model, UC, which can be interpreted as the optimal planning objectives. This approach may not have a viable solution in the UC, because the differences and/or approximations could lead to the non-viability of the set of objectives established by the DP for the UC. There are two alternatives to carry out coordination. Coordination through economic variables, dual variables or prices. To this end, the opportunity value of inventories is set at the end of the period TCP, or at the beginning of the first period. In this case, it corresponds to the value of the water. The application of this approach should be careful, as boundary conditions should reflect variation in prices between periods, but in general, only a sample of the value of water is considered, at the beginning or at the end of the planning horizon. This can lead to water value profiles, which are far removed from the profile estimated by the DP model, which is never observed in the UC. This approach always offers viable solutions, but they may be far from optimal due to the distortion of the dynamic price profile. Coordination through physical variables, primal variables or quantities. To this end, the quantities of resources to be used and the quantities of industrial products to be produced during the period of operation of one to the same period are established. The inventory levels that must be reached at the end of the period, the TCP moment, are also established. This approach does not distort the dynamic price profile but may not have a viable solution due to the small differences between the two models. Non-feasibility, which can be managed by soft constraints, which introduce penalized slack in the target function, to ensure that the final schedule is close to the optimal target set by the planning. The chaining, or coordination, of models does not guarantee optimality, because there are always at least two alternatives to concatenate two models. By quantities, or primal variables, such as water use, or resource use in general, or by prices, or dual variables, that is, the value of water, or in general the value of resources. Cyclical coordination can produce the optimal solution, or correct unfeasible solutions. The integrated model can be solved using large-scale techniques, such as Bender's partitioning and Lagrangean relaxation. This approach reduces solution time and memory requirements. It can be said that the approach presented corresponds to a version of Industry 4.0, and that the change experienced until Industry 6.0 is very large, having affected the way of implementing mathematics, which is different from having changed mathematics. However, one of the most impactful changes occurs with the arrival of the Internet of Things, IoT, typical of Industry 4.0, which began to change the models that ran at discrete frequencies, such as days, weeks, months, for real-time models, which are the ones that should be used today. Distributed economic dispatch. The coordination of two types of models are studied, economic dispatch and unit commitment. The problem will be analyzed from the point of view of Lagrangean relaxation. Lagrangean relaxation. Lagrangean relaxation is a mathematical technique used to solve complex problems of constrained optimization, simplifying them into relaxed versions that are easier to solve. It is especially effective for combinatorial optimization problems where a few hard constraints make the original problem computationally intractable. The method follows a divide-and-conquer philosophy. The steps to follow are: identify difficult constraints. Constraints are divided into two groups: easy constraints that can be resolved quickly, and hard constraints, lateral constraints that complicate the structure. Dualize with penalties. Hard constraints are removed from the constraint set and moved to the target function. Lagrange multipliers. Each relaxed restriction is multiplied by the Lagrange multiplier, which acts as a penalty for violating the restriction. The process to follow is: relaxed problem. For any fixed set of multipliers, solving the relaxed problem is usually easy. Quote generation. The solution to the relaxed problem provides a limit to the optimal value of the original problem, a lower limit for minimization, an upper limit for maximization. Lagrangian dual. To find the best possible bound, we solve a secondary optimization problem, the Lagrangian dual, which seeks to maximize the lower bound, or minimize the upper bound, by iteratively adjusting the multipliers. Updating multipliers. The subgradient method is often used to update multipliers, moving them in a direction that penalizes current constraint violations. It can also work with cutting planes. To model Lagrangian relaxation, LR, two questions must be decided. First, what constraints to relax to define the subproblems, and second, the strategy for updating the Lagrange multipliers. The objective function, together with the local min constraints, define the upper Lagrange bound problem. By relaxing these constraints, the problem can be separated into a subproblem for each cluster. The problem of economic dispatch uses a monolithic model that is traditionally solved by large-scale optimization techniques. This problem can be solved in parallel, but it remains monolithic. Bender's decomposition is the most widely used and most recognized theory in solving DP and UC problems. To solve the problem, a master model and several subproblems are designed that establish an exchange of dual and primal variables. The master problem sends primal variables to the subproblems. Bender's theory works in the primal feasibility zone. Lagrangian relaxation is the alternative to Bender's theory and uses a similar architecture. To solve the problem, a master model and several subproblems are designed that establish an exchange of dual and primal variables. The master problem sends dual variables to the subproblems. Lagrangean relaxation theory works in the dual feasibility zone. However, Lagrangean relaxation is the basic theory of DP and UC in Industry 6.0. The problem of Lagrangean relaxation must be broken down into 4 problems. Master problem, in charge of coordinating the subproblems, and 3 subproblems, 1 for each entity of the system. To solve the problem, a conversation is established between the master problem and the subproblems. The coordinating problem sets values of the dual variables, marginal costs, and the subproblems return information based on the primal variables. LR worked in the non-feasible zone of the primal variables, and in the feasible zone of the dual problem. In this case, Lagrange theory indicates that there is only one Lagrange multiplier and, therefore, it must be equal in all subproblems. The convergence of the integrated problem is achieved when in 2 consecutive iterations, the value of the Lagrange multipliers remains constant. The image presents the use of Lagrangean relaxation to solve the smart grid problem. Each subproblem corresponds to a smart grid, and the master problem is equivalent to the smart grid control center. The relaxed restrictions on all smart grids are the demand for energy, and the generation of energy, and if applicable, it must balance purchases and/or sales with the utility linked to the smart grids. Marginal costs indicate the price of energy for each period. Autonomous Lagrangian relaxation. Consensus algorithms. Autonomous Lagrangian relaxation theory. LR is about solving the monolithic problem using large-scale optimization methodologies. Although the solution process may be parallel, the problem remains integrated and requires a coordination problem. ALR is about using a consensus algorithm so that each problem is solved independently, and the solution is obtained through a consensus among the players participating in the game. The rules of consensus are based on the Lagrange theory. There is no monolithic problem, there are n independent problems. To determine optimality, the advanced metering infrastructure, AMI, of all electric systems must match. To do this, each electric system knows all the AMIs and moves towards the Lagrange multiplier solution. The electric systems will move autonomously, following logical rules that guarantee convergence, for example, moving towards the average of the Lagrange multipliers. For static processes, this consensus rule ensures that the problem will be optimal. Considering that LR is a primal non-feasible method, to use its results at any time, it is necessary to implement a mathematical problem that recovers the primal feasibility. In this case, it is a matter of recovering the feasibility of the demand and the generation equations. The feasibility recovery problem can be independent and reside in the AMI. To do this, it is necessary to implement an empirical rule of consensus based on optimization. The evolution of Lagrangian relaxation, LR, in Industry 6.0 has been named by High as Autonomous Lagrangian Relaxation, ALR. ALR is based the mathematical principles of Lagrange theory but is aimed at modeling living intelligent systems, which are autonomous and do not require coordination problems. On the other hand, its greatest strength is the modeling of systems in real time, based on intelligent sensors. ALR can also be called distributed Lagrangian relaxation, DLR. To differentiate itself from distributed Lagrangian relaxation, DLR, Lagrangian relaxation can be called centralized Lagrangian relaxation, CLR, since the model remains monolithic, and is solved in parallel using large-scale optimization technologies. ALR is based the mathematical principles of Lagrange theory but is aimed at modeling living intelligent systems, which are autonomous and do not require coordination problems. On the other hand, its greatest strength is the modeling of systems in real time, based on intelligent sensors. ALR is about using a consensus algorithm so that each problem is solved independently, and the solution is obtained through a consensus among the players participating in the game. The rules of consensus are based on the Lagrange theory. There is no monolithic problem, there are n independent problems. To determine optimality, the advanced metering infrastructure, AMI, of all electric systems must match. Consensus algorithms. Consensus algorithms are fundamental to the operation of decentralized networks, mainly blockchain networks. They ensure that all network participants agree on the validity of transactions and the state of the blockchain. Without consensus, there would be discrepancies in the data between different nodes, which could lead to fraud and errors. These algorithms facilitate trust between users who may not know or trust each other, allowing decentralized systems to function effectively. Different consensus mechanisms have been developed to respond to the needs of various applications, each with its own strengths and weaknesses. Validate transactions and add them to the database. Prevent double spending and fraudulent activities. Improve network security against attacks. Optimize network performance. Allow decentralized decision-making. There are several types of consensus algorithms, each designed to address specific needs and challenges within distributed and autonomous network technology. Each type employs different mechanisms to achieve consensus, thus influencing the overall efficiency and scalability of the network. Understanding the particularities of each can help determine which one is best suited for specific applications. The most widely recognized types are: proof of work requires participants to solve complex mathematical problems. Proof of stake allows validators to create new blocks based on the power they possess. Delegated proof of stake involves selecting some nodes to validate transactions on behalf of others. Practical Byzantine fault tolerance errors focuses on achieving consensus despite failures or malicious actors. Proof of authority relies on a limited number of trusted nodes to validate transactions. The importance of consensus algorithms cannot be underestimated, as they provide the backbone for the reliability of autonomous and distributed networks. They ensure that all participants maintain a unified view of the network, which is essential for transparency and accountability. These algorithms protect the network from various types of attacks, such as Sybil attacks, where a malicious actor creates multiple identities to take control of the network. The choice of algorithm can significantly affect the speed and scalability of transactions. Therefore, selecting the right consensus mechanism is a critical factor in the design of a decentralized system, because they establish a safe and reliable way to reach an agreement, minimize the risk of network forks, which can lead to confusion, allow the system to function without a central authority, dictate how quickly transactions can be processed, and influence the costs associated with maintaining the network. While consensus algorithms are essential, they also come with their own challenges. A major issue is scalability, as many algorithms struggle to efficiently handle a growing number of transactions. Some consensus mechanisms, such as proof of work, POW, have been criticized for their high energy consumption and environmental impact. Security is another concern, as vulnerabilities in the algorithm can lead to exploitation and attacks. Achieving consensus in a decentralized environment can introduce latency, affecting the overall performance of networks in real time. These challenges require continuous research and innovation in the field of consensus mechanisms. Some problems to be solved are: scalability issues can lead to slower transaction times. Energy consumption is a significant concern for POW systems. Security vulnerabilities can expose the network to attacks. Latency can affect the user experience during high traffic periods, and continuous improvement in algorithms is necessary for adaptation. The future of consensus algorithms is promising, with continued advances aimed at addressing current limitations. Innovations such as hybrid consensus models are emerging, which combine diverse algorithms to leverage their strengths while mitigating weaknesses. Research on more energy-efficient consensus mechanisms is gaining traction, focusing on sustainability. As autonomous networking technology evolves, we can expect a greater emphasis on scalability and speed, ensuring that decentralized systems can compete with traditional centralized solutions. The development of new consensus algorithms will play a key role in shaping the future landscape of autonomous networks. Hybrid models can enhance performance and reduce energy use. New protocols are being developed for faster transaction times. Research into quantum-resistant algorithms is on the rise. Community governance may influence future algorithm designs, and the integration of artificial intelligence may optimize consensus processes. Consensus algorithms are vital to ensure the reliability and security of real-time networks, such as smart grid networks and blockchains, as they facilitate agreement between decentralized participants, enabling transparent and reliable transactions. While challenges remain, innovation still promises to improve the scalability, efficiency, and sustainability of networks in real time. As the landscape continues to evolve, understanding these algorithms will be essential for developers, users, and stakeholders in the distributed operations ecosystem. In smart grids, consensus algorithms are used to coordinate distributed decision-making among multiple agents, like smart meters, microgrid controllers, distributed generators, without relying on a central authority. They are crucial for distributed energy management, economic dispatch, voltage/frequency control, and peer-to-peer energy trading. The distributed economic dispatch are the future of the new generation of dispatch models, which must evolve towards autonomous and distributed architectures, typical of Industry 6.0. Smart grids. Distributed economic dispatch. The case of the distributed economic dispatch of smart grids was one of the first cases known to HI, which will be analyzed. Each smart grid requires a specific decision support system that allows the operator to interact with the entire electricity system. Starting from the original electrical system, a wholesale electricity market. Smart grids were advancing little by little, initially seen as isolated systems. Currently, these electrical systems must coexist and interact with each other. The centralized control of the system focused on the development of assets, hardware and software, for the wholesale electricity system. Under the concept of OpTeX, Optimization Expert System, the software is built using layers of equations that are integrated to build the models. The current models of dispatch planning, DP, and unit commitment, UC, can be used for current smart grids, making the necessary scale and regulation adjustments. Challenge: modify the centralized economic dispatch to a distributed economic dispatch to enter the Industry 6.0 environment. Solution: it implies that all agents must know what information they need to obtain from the Advanced Metering Infrastructure Systems, AMI, what information they must provide to other agents to make their decisions, and thus keep the end-to-end system on the path to optimality. This is possible using asynchronous autonomous real-time distributed methodologies, like autonomous Lagrangean relaxation. Methodology: in the case of regional smart grids, the process of planning or scheduling electricity systems could be carried out as follows. The connection topology of smart grid networks is developed according to the criteria of a central coordinator, the regulation, and/or the autonomous decisions of the agents. The mathematical models running on each smart grid correspond to the currently tuned models, DP and/or UC, but in general they are the same models that are currently used. The adjustments of the models are related to scale or regulation details. This network does not require a physical coordinator, as the models run independently on each smart grid and coordinate autonomously, and the coordination of the models can be done by prices or by quantities, which will be the consensus methodologies. The integrated model can be solved using large-scale techniques, such as Bender's partitioning and Lagrangean relaxation. This approach reduces solution time and memory requirements. The solution of the UC or PD problem is independent of the conception of the distributed dispatch system. Within each smart grid, the optimization problem can be solved monolithically or use large-scale optimization techniques, such as Bender's and Lagrange's decomposition theories. The two methods of coordination are valid mathematical methodologies, either by prices or by quantities. The system coordinator must choose one of the two. Perhaps it is better that it is regulated, because all smart grids must coexist autonomously and independently in the same region, but following game rules. Coordination by quantities is more complicated, because it is not a variable common to the subsystems. Coordination by prices seems easier and is a well-known rule in economics. Optimal marginal costs, without restrictions, must be the same in all smart grids. This is a consensus scientific rule, which has been well studied and cannot be questioned, since it is not an opinion. This is HI's proposal. The art of optimization in Industry 6.0 is to eliminate the coordinating model and replace it with a consensus rule. In this case, the consensus rule is that, in the absence of constraints, the marginal cost must be the same in all smart grids, following Lagrange's laws. If there are constraints, the consensus must follow the laws of Karush, Kuhn, Tucker, KKT. Models with different methodologies, or technologies, of solution can coexist. The approach can be conceived as an artificial brain composed of a network of mathematical models, a model for each smart grid and for each site of large generation and/or consumption. Communication between the algorithms of mathematical problems must be asynchronous when events occur in the system. This can be continuous. For optimization purposes, the artificial brain does not need a coordinator, as the smart grid system acts autonomously and independently. However, in order to function as a technical control and regulatory control, it may be necessary to have a system supervisor. The Industry 6.0 artificial brain does not require a system supervisor. Operational planning and unit commitment. A well-known activity in the electricity sector is the coordination of two fundamental models: economic dispatch, or operational planning, DP, and unit commitment, UC. Starting from the original electrical system, a wholesale electricity market, smart grids were advancing little by little, initially seen as isolated systems. Currently, these electrical systems must coexist and interact with each other. The centralized control of the system focused on the development of assets, hardware and software, for the wholesale electricity system. The emergence and development of smart grids generates a distributed control of the system, in which many islands, which initially operate in isolation, must be coordinated. Technological evolution has given rise to total distributed control, in which multiple types of electrical assets coexist and communicate with each other. Smart grids have generated communities of users that consume and generate energy and require a broad control system that unites all the production-consumption cells that the electricity system has. It is a system like the Internet, where the autonomous communities share physical resources and communicate with each other, which gives greater power to the physical system, but requires more advanced artificial intelligence to manage it. Under the concept of OpTeX, Optimization Expert System, the software is built using layers of equations that are integrated to build the models. The current models of dispatch planning, DP, and unit commitment, UC, can be used for current smart grids, making the necessary scale and regulation adjustments. Autonomous real-time distributed economic dispatch. Challenge: modify the traditional centralized economic dispatch through a distributed economic dispatch to enter the Industry 4.0 environment. Solution: it implies that all agents must know what information they need to take from smart metering systems, and what information they must provide to other agents to make their decisions, to keep the end-to-end system on the optimality path. This is possible using asynchronous parallel optimization methodologies. Methodology: in the case of regional smart grids, the process of planning or scheduling electricity systems could be carried out as follows. The connection topology of smart grid networks is developed according to the criteria of a central coordinator, the regulation, and/or the autonomous decisions of the agents. The mathematical models running on each smart grid correspond to the currently tuned models, DP and/or UC, but in general they are the same models that are currently used. The adjustments of the models are related to scale or regulation details. This network does not require a physical coordinator, as the models run independently on each smart grid and coordinate autonomously, and the coordination of the models can be done by prices or by quantities, which will be the consensus methodologies. The integrated model can be solved using large-scale techniques, such as Bender's partitioning and Lagrangean relaxation. This approach reduces solution time and memory requirements. The two methods of coordination are valid mathematical methodologies, either by prices or by quantities. The system coordinator must choose one of the two. Perhaps it is better that it is regulated, because all smart grids must coexist autonomously and independently in the same region, but following game rules. Coordination by quantities is more complicated, because it is not a variable common to the subsystems. Coordination by prices seems easier and is a well-known rule in economics. Optimal marginal costs, without restrictions, must be the same in all smart grids. This is a consensus scientific rule, which has been well studied and cannot be questioned, since it is not an opinion. This is High's proposal. Coordination by prices seems easier and is a well-known rule in economics. Optimal marginal costs, without restrictions, must be the same in all smart grids. This is a consensus scientific rule, which has been well studied and cannot be questioned, since it is not an opinion. This is High's proposal. Coordination by prices seems easier and is a well-known rule in economics. Optimal marginal costs, without restrictions, must be the same in all smart grids. This is a consensus scientific rule, which has been well studied and cannot be questioned, since it is not an opinion. This is High's proposal. Models with different methodologies, or technologies, of solution can coexist. The approach can be conceived as an artificial brain composed of a network of mathematical models, a model for each smart grid and for each site of large generation and/or consumption. Communication between the algorithms of mathematical problems must be asynchronous when events occur in the system. This can be continuous. For optimization purposes, the artificial brain does not need a coordinator, as the smart grid system acts autonomously and independently. However, in order to function as a technical control and regulatory control, it may be necessary to have a system supervisor. The Industry 6.0 artificial brain does not require a system supervisor. Distributed economic dispatch applications. One of the most impactful changes occurs with the arrival of the Internet of Things, IoT, which began to change the models that ran at discrete frequencies, such as days, weeks, months, for real-time models. It can be said that in Industry 6.0 all models work in real time, so that the world reacts distributed and online, for all IoT-connected systems. For static systems, the methodology is also valid, but the world is dynamic. IoT enables all models associated with Industry 6.0. Dispatch of an agro-industrial supply chain. Normally, an agro-industrial chain must be planned integrally, which involves coordinating many farms. IoT facilitates the knowledge of the status of each farm, in such a way that each of them can be planned autonomously and independently, following the principles of Industry 6.0. Another point of view is the spatial distribution of the problem. In this case, an artificial hypothalamus is presented for an agro-industrial company that has multiple facilities, farms, concentrated food factory, meat products factory, and stores in the food market. Dispatch of large multi-business global company. The example corresponds to an oil company, which covers all the streams in the oil chain, which are expected to be connected to IoT. In 2009, High implemented an artificial brain following the methodology available at the time. The model was designed to be used monthly. Today, under Industry 6.0, the artificial brain should run online. According to the structure of modern electricity markets, the support of the business decision-making power generation should be seen from several points of view. Central agents, formed by the regulator, supervisor, planner, and system operator. Generators, agents that operate power plants. Distributors, utilities enterprises. Traders, smart grids operators, and industrial companies. High-UL, high-SGO and high-gas together and make high-power that is set simulation models optimal dispatch of electricity and gas systems. High-UL, electricity supply chain optimization, models designed to support the decisions of the various actors involved in the electricity supply chain. High-SGO, smart grids optimization, models designed to support the decisions of the various agents involved in the smart grids business. High-gas, natural gas supply chain optimization, models designed to support the decisions of the agents involved in the natural gas supply chain. High-UL and high-SGO cover all levels of the electricity systems. Dispatch of multi-business energy enterprise. The artificial brain of a multi-business energy enterprise is the result of the integration of mathematical models of predictive and prescriptive analytics of several subsystems. Hydro system, electricity system, natural gas systems, and smart grid systems. The models supplied by HI, since 1998, have been designed following the principles of Industry 4.0, using monolithic models solved using large-scale optimization methodologies. Under Industry 6.0, the models should run online, all the time, taking advantage of the IoT of all systems. Dispatch of network of smart grids. For large smart grid systems, this is the only way to solve the problem, and all types of components of the network can coexist. It is applicable at the utility level, or to integrate them into the interconnected system. Planning and scheduling is one of the main functions in an energy system. In the case of electricity, two models are involved: stochastic economic dispatch model, and deterministic unit commitment model. The tradition has been to run the models periodically, for example, every day. However, nowadays models can work permanently online. Dispatch of stochastic economic dispatch model. The solution to this problem involves creating a version of the model for each scenario, and solving all of them autonomously and independently, based on coordination on consensus rules. Dispatch of planning and scheduling of electric systems. The deterministic unit commitment model must be integrated with the stochastic economic dispatch model. The models must work permanently online to guarantee the unit commitment function. In an electric company, more than one function is performed and planned simultaneously. Some functions must be performed online and others periodically. Consider the case of an electric company that operates 6 of the models available at high power. The models are economic dispatch, unit commitment, financial analysis, maintenance optimization, electricity supply chain design, and ETRM, energy trading and risk management. Dispatch of network of functions. Together, all the models make up the artificial brain of the company, which must be working permanently, to attend to any event that occurs in the organization, or in its environment. ARCAD is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information, you can consult the URL. As George Bernard Shaw would say, "You see things, and you say, why? But I dream things that never were. And I say, why not? HI dreams models that never existed and wonders, why not?" This free thinking has made HI a leading company in decision-making artificial intelligence. Thank you for your attention.